students, Ampere's circuital law. Actually, what is Ampere's circuital law? It states that the closed line integral of magnetic field intensity is equal to the total current enclosed. Enclosed means inside, students. Total current enclosed, that means inside. Total current enclosed by that closed line. So mathematically it was closed H dot dl is equal to I enclosed. This was the equation. I told you this is ampere per meter multiplied with meter gives ampere. Ampere means current. So here there is a closed line. Inside a closed line, open surface is present. Now simply for the purpose of Maxwell equation, let us say total current is I. Then this becomes closed H dot dl is equal to I. This is equation number 1. We are assuming that current inside the closed line is I. For example, here there is a conductor carrying I current. Then you put the thumb in current direction. Then H bar is there on this line. H bar is there on this line. Now, if you calculate like this, no, H bar is there. This is a closed line. This is a closed line. On this closed line, H bar physical quantity is there. Now, if you calculate closed H dot dl bar on this line, this is a circle means closed, L means line. This is a closed line on which H bar physical quantity is there. Now, inside this, how much current is there? I current is there. Now, this is equal to I you get. So, that's what I was telling here. Now, I told you inside a closed line, open surface is there. So, write current in terms of open surface. By definition, current crossing the open surface is current crossing the open surface is I is equal to double integral j bar dot ds bar. This is equation number 2. Now, from Stokes theorem, closed H bar dot dl bar is equal to double integral del cross H dot ds bar, equation number 3. So, put equation 2 comma equation 3 in 1. Then we get double del cross H bar dot ds bar is equal to double j bar dot ds bar. Now, compare both sides. Then we get del cross H is equal to j bar. This is equation number 4. This is called Maxwell equation. Del means dou by dou x, dou by dou y, dou by dou z. That means differentiation. This is called differential form of the Maxwell equation. Now, this equation came from Ampere's circuital law. Then Maxwell observed here there is no time term. Then Maxwell understood that this is valid only for static field. He understood. That means some term is missing. He understood, because d by dt is not there. That means it is not valid for time varying fields actually. Now Maxwell understood, and he wanted to modify this, and he has modified. That is why these equations are called Maxwell equations. So dear students, here equation 4 is valid for static fields. Now for time varying fields, Maxwell modified this equation, and how he has modified, just I will write in the box here. So here some term is missing, time varying term. Then he has taken del cross h is equal to j plus some unknown he has taken. Now after taking unknown, let us say this is equation number 5. Now he took both sides um, divergence, take divergence both sides. Now divergence of del cross h bar is equal to divergence of j bar plus divergence of this unknown vector. Now from mathematics, divergence of curl of any vector is always 0. That is equal to divergence of j bar plus divergence of some unknown. So let us say this is equation number 6. Continuity equation is divergence of j bar is equal to minus of dou rho v by dou t. So this one is equation 7. Now put equation 7 in equation 6. In place of divergence of j, you can write this one. 0 is equal to minus dou rho v by dou t plus divergence of this unknown vector. So you can send this side. So divergence of unknown vector is equal to dou rho v by dou t. So this equation number 8. Now also we know that one of the Maxwell equation, divergence of d bar is equal to rho v. This is 9. So here put equation 9 in 8. So divergence of unknown quantity is equal to, here rho v is divergence of d bar. Now divergence of unknown vector is equal to divergence of dou d bar divided by dou t. Compare both sides. So compare both sides. Then unknown vector is equal to dou d bar by dou t. You got. So ultimately this is equation number 10. So put equation 10 in equation 5. So del cross h is equal to j bar plus that unknown vector is dou d bar by dou t. This is all I am putting in the bracket. This is rough work. Don't bother about that one. So this is rough work, students. Okay. So here we were here. So this equation is valid for static fields because here there is no d by dt. That means the time term is not there. Now I am writing here Maxwell modified equation 4 by adding dou d bar by dou t. Okay, for time varying fields. You can see here dou by dou t means differentiation with respect to time. If you are differentiating with respect to time, means it should be a function of time d. If d is a function of time, that means electric field is a function of time. That is the meaning. Of course, then magnetic field will be a function of time because time varying electric field generates time varying magnetic field. Time varying magnetic field generates time varying electric field. They are interactive. So now final equation for time varying fields is del cross H is equal to J bar plus dou d bar by dou t, students. So Maxwell modified Ampere circuit law, because this equation came from Ampere circuit law. Maxwell modified Ampere circuit law, and while modifying he has used the continuity equation. Then he has added the term called dou d bar by dou t. You remember these things. Maxwell modified Ampere circuit law. If you want, you can write Maxwell modified Ampere circuit law, and while modifying he used a continuity equation, and then finally he has added the term called dou d bar by dou t. So this is current density. Beside that, you are adding something, means that is also current density. You can see here, this is Coulomb per meter square. D by dt of Coulomb is ampere, so ampere per meter square, this is current density. Already we know that d bar is a displacement flux density. Then you differentiate that, you get displacement current density. So this is called actually J is equal to sigma E bar, conduction current density, and D is equal to epsilon E. So epsilon dou E bar by dou t. This is called JC bar, conduction current density. This is called displacement current density. Now if you add them, that is called total current density. It is called total current density. So here you have to remember this equation. And from where this equation came, dear students? It came from Ampere circuit law, but Maxwell modified this by adding dou d bar by dou t. Here Jc is equal to sigma E bar. This is conduction current density. So unit is ampere per meter square. Then Jd bar in time domain is equal to dou d bar divided by dou t. D is equal to epsilon E. So this is called displacement current density. Now Jt bar is total current density actually. Total current density. Okay. So anyway, I will be writing these equations. Till now we have seen two Maxwell equations for time varying fields. But for static fields, d is not a function of time. Then d by dt becomes 0. Then del cross h becomes j. We will write that later on in the note. Now, till now we have seen two Maxwell equations, and third Maxwell equation came from Gauss law of electric field. So Gauss law of electric field. Already you know that if there is a q charge here, then from that in every direction electric flux goes away. Then total electric flux is equal to total charge from which that is generated. So if you take a closed surface, then double integral d bar dot ds bar, you have taken a closed surface here, so double closed d bar dot ds bar gives a total charge inside this, so that is equal to q. This is called actually Gauss law of electric field. Okay, what is this? Electric flux by area multiplied with area, it gives electric flux. Circle means closed, S means surface. Electric flux crossing closed surface is equal to total charge inside this closed surface. So this is the mathematical equation of the Gauss law of electric field. Okay, students. Now double closed d bar dot ds bar is equal to q. Here this is the mathematical equation of Gauss law of electric field. This is equation number 1. By definition, closed surface, inside a closed surface volume is present, so write charge in terms of volume, then you get Q is equal to triple integral rho V dV. This is equation number 2. And also from divergence theorem, double closed d bar dot ds bar is equal to triple integral divergence of d bar of dv. This is equation number 3. Put equation 2 comma 3 in equation number 1, then triple integral divergence of d bar dv is equal to q is triple integral rho v dv. Compare both sides, then you get divergence of d bar is equal to rho v. This is one of the Maxwell equation, dear students. Now this is called integral form of that equation because integration is there with respect to distance. Here this is called differential form of the Maxwell equation. We will write them in the note. Now we have to understand this equation, Maxwell equation, came from Gauss law of electric field actually. So this is third Maxwell equation. Now fourth Maxwell equation came from Gauss law of magnetic field. Already I told you, if you take one magnet like this, then this is north pole and south pole, and this one is magnet. From the north pole, magnetic flux comes out, then again it goes internally. So this is magnetic flux. Okay. Now B is defined as magnetic flux divided by area. This volume has 6 surfaces. It is like a cube. Of course, it is not cube, and it has 6 surfaces. It is like your room. It has 6 surfaces. So 6 surfaces are there, means it is called as closed surface. Inside this closed surface, volume is there. So this is a closed surface. Now if I take a double b bar dot ds bar closed, then what you get here, this definition b bar means magnetic flux by area, multiply with area, then you get magnetic flux. Circle is there, that means magnetic flux crossing closed surface you get. So now what is the magnetic flux crossing the closed surface? Let us see now. Here one flux line is going out, again it is coming back, so net outflow is 0. For example, it is a room, one student is going out. How many students went? One student. Then again that student is coming back, again entering into this room. So how many number of net outflow of students? 0 actually. So in this way you get answer 0. So dear students, this is the mathematical equation of Gauss law of magnetic field. So this is magnetic flux by area into area gives magnetic flux. Circle means closed, S means surface, magnetic flux crossing the closed surface. Now here one flux line is going out, it is entering again, so net outflow is 0. In this way so many flux lines go out, again they come back, so that net outflow is 0. So this is called Gauss law of magnetic field. Gauss law deals with closed surface. This is Gauss law of magnetic field. Similarly, here also this is electric flux. For example, D is defined as electric flux by area. So electric flux by area. Now double closed d bar dot ds bar means electric flux by area into area gives electric flux. Circle means closed, S means surface. This gives electric flux crossing the closed surface. Now here electric flux is going out like this from positive charge. Electric effect or otherwise electric flux goes out. Then experimentally it is found that total electric flux going out of this closed surface is equal to total charge inside that. Total charge inside that is Q. That means meaning is this electric flux is generated from this total charge only. It goes out, and wherever negative charge comes, it ends there. So this closed surface K means that is called Gauss law. You are dealing with electric quantity, so Gauss law of electric field. Here you are dealing with magnetic field and closed surface. It is called Gauss law of magnetic field. Okay. Here integration is there, so that is why it is called integral form of Maxwell equation. Now from the divergence theorem, if you see carefully, so students, now this one Gauss law of magnetic field is this one. Actually double closed B bar dot ds bar is equal to 0. So I am writing here double closed B bar dot ds bar is equal to 0. Now from divergence theorem, double closed B bar dot ds bar is equal to triple integral divergence of B bar dv, equation number 2. So put this equation 2 in equation number 1, then you get triple integral divergence of B dv is equal to 0. Compare both sides. Compare both sides. Then you get divergence of B bar is equal to 0. So this is the equation number 3. So here del is there means differentiation. So this is differential form of Maxwell equation, and this is integral form of Maxwell equation. This Maxwell equation came from Gauss law of the magnetic field. So till now, whatever you have studied, I am writing in the note, so you have to remember them. Now, Maxwell equations for time varying fields. From which law each Maxwell equation came? First one is Faraday's law. Okay. Second one is Ampere circuit law. Now here integral form. So from Faraday's law, integral form equation is this one: closed E bar dot dl bar is equal to double integral minus of dou b bar by dou t dot ds bar. Now differential form or otherwise it is also called as a point form. Okay, that was del cross E bar is equal to minus of dou b bar by dou t. Okay. Here from Ampere circuit law, closed h bar dot dl bar is equal to, you got double integral j bar dot ds bar plus double integral dou d bar divided by dt dot ds bar, and this gives actually conduction current density multiplied with area gives conduction current, and then displacement current density multiplied with area, it gives displacement current. Okay, you can write like this also. Now in the differential form, del cross h bar is equal to j bar plus dou d bar divided by dou t. So this is the conduction current density, this is displacement current density. So this is Jc bar plus Jd bar. Okay. Now third Maxwell equation came from Gauss law of electric field. So here that is double d bar dot ds bar is equal to triple integral rho v dv, or otherwise that is also written like this, double integral d bar dot ds bar is equal to q. Now this came divergence of d bar is equal to rho v. Gauss law of magnetic field is double closed b bar dot ds bar is equal to 0. So divergence of b bar is equal to 0 you got. Now this Maxwell equations for static fields. Maxwell equations for static field is obtained by putting dou by dou t is equal to 0 in above equations. So because for static fields these electric and magnetic quantities are not functions of time, then if you differentiate with time they become 0. So in this table if you substitute d by dt 0, here also 0, here it is 0, here 0, then you get the Maxwell equations for static field. Okay, now I am writing here. First one is Faraday's law. From Faraday's law, integral form, and then differential form. So this equation is simply closed E bar dot dl bar is equal to 0 and del cross E bar is equal to 0 you get, because dou by dou t is 0. Actually dou by dou t means partial differentiation with respect to time, because B bar can have distance parameters also. You should not differentiate with respect to distance. You have to differentiate only time parameter only. That is the meaning of dou by dou t. So second one is Ampere's circuital law. Ampere's circuital law. Here this becomes 0. So closed h dot dl bar is equal to double integral j bar dot ds bar, simply that is written as I. So closed h dot dl bar is equal to I. Now del cross h bar is equal to j bar only, because dou d by dou t becomes 0, and these equations are not going to change, they come as it is. Gauss law of electric field, d dot ds is equal to q. Now divergence of d is equal to rho v. Gauss law of magnetic field is double B bar dot ds bar is equal to 0 and divergence of B bar is equal to 0. So that table you have to remember, and anyway no need to remember this table, because in the table if you put d by dt 0, you get this one. Okay, now let us solve some questions based on time varying fields and Maxwell equations. So dear students, now let us solve the questions. The first question is, a varying magnetic flux linking a coil is given by, this is actually magnetic flux equation is given, it is a function of time. If at time t is equal to 3 seconds, the EMF induced is 9 volt, then the value of lambda is. Actually, EMF is equal to minus of d by dt of magnetic flux. That means EMF is equal to minus of d by dt of, this is 1 by 3 lambda t cube. So EMF is equal to minus 1 by 3 lambda is constant, d by dt of t cube is 3 t square. So EMF at t is equal to 3 second is equal to, this 3 cancel, minus of lambda into t is equal to 3, so 3 square you have to substitute. Now it is given that EMF induced is 9 volt at t is equal to 3 second, so it is given as 9 volt. Now that is equal to minus lambda into 9, so lambda is equal to, you get minus 1. Okay, if you want units, lambda is equal to, magnetic flux is Weber per second cube actually, so Weber per second cube. If you want units from this, no, this is Weber, this 1 by 3 no unit, and t cube means second cube, so Weber per second cube, right students? That in answers print means is there the unit, so this is the answer. Now a parallel plate air filled capacitor, air filled means for air filled capacitor epsilon naught is there, so it is air filled capacitor, has plate area 10 power minus 4 meter square and distance between the plates d is equal to 10 power minus 3 meter, and it is connected to a voltage source Vs is equal to 0.5 volts, then frequency is equal to 3.6 into 10 to the power giga means 10 power 9 dear students, so 10 power 9 Hz. Okay, source, the magnitude of the displacement current is, the magnitude of the displacement current is. So dear students, actually already you know two formulas, JD of t is equal to dou t bar divided by dou t. Actually it is in time domain. Now whenever frequency is given in the question, you have to write that in frequency domain or otherwise in steady state domain. So that is like network theory concept. So in steady state domain we will write this as a J D S. S stands steady state or otherwise frequency domain. In steady state d by dt is replaced with j omega, d is written as ds. S stands steady state here. Now JD of S is equal to, actually displacement current density definition is displacement current divided by area, so that is equal to j omega, d is equal to epsilon E, so this is the formula. So actually this is the formula of displacement current density in time domain. In any question electric field is given, d is equal to epsilon E, actually electric field is given in terms of time, then you want displacement current or otherwise displacement current density, you have to use this formula. In any question frequency is given, then that person is talking of displacement current density or otherwise displacement current, then you have to use these formulas. Okay, now in this question frequency is given and he is asking displacement current magnitude, so you have to use this formula, and displacement current density is required, you use this, displacement current is required. Now you know displacement current density is equal to displacement current by area actually. So displacement current ID, yes, I means current, D means displacement, S means in steady state. So by area is equal to J, omega is 2 pi f actually, then epsilon for air field, epsilon is equal to epsilon naught ES bar. Okay, so that implies IDS is equal to J 2 pi f, then epsilon naught, then electric field in magnitude form I am writing. Okay, so this is, if you take vector here, here also vector. If you take magnitude of this, you take here magnitude of that. Anyway, I am putting this vector, and here I am taking magnitude this side also magnitude. Now electric field is equal to voltage divided by distance between the plates, and ID by area was there, area comes this side. So here, now all are given, frequency is given here, and epsilon naught, you know, Vs is given 0.5, D is there, distance between the plates is there, area also given, you substitute, you get IDS, magnitude is required, you take modulus. So IDS is equal to J into 2 pi into frequency is given as 3.6 into 10 to the power 9, and epsilon naught is 1 by 36 pi into 10 to the power minus 9, that is epsilon naught. Vs is given as 0.5. Now distance is 10 to the power minus 3 here, and area is 10 to the power minus 4. So from this, here pi cancel, then 3.6 by, that means denominator 10 remains, this gone. So now denominator 10 is there, 2 by 10 is there, then here it comes that here J 2 is there, and pi cancel, 10 power minus 9, 10 power minus 10 power plus 9 gone, and 2 by 10 is there. Then what else is there here? Here 10 power minus 1 is there, and this is 5. So 5 into 10 to the power minus 2 is there here. That is equal to J, this is 10 into 10 to the power minus 3 ampere. Okay. Now you want modulus of IDS, that is nothing but 10 milliampere. Okay, 10 milliampere is the answer. Okay. Now you see this question. In this question, two conductor coils, coil 1 and coil 2, are given like this. So these are the magnetic field lines, and one coil is there, conductor coil, it is given like this, that is perpendicular to the magnetic field he has given. The plane of the coil, this is the coil actually, conductor circular loop or otherwise coil, that plane is this one, this plane is perpendicular to the magnetic field lines. So here in the question B of T is given. Now already we have studied, if magnetic field is perpendicular to the coil, then in this coil EMF is induced. So here two coils are there, one coil is like this, it is closed, other coil is split coil. Split means there is a open cut here, split means cut is there, open, that is. So one coil is like this, other coil is like this. Now whenever coil planes are perpendicular to the magnetic field, then in both of them EMF is induced. Already I told you, dear students, for example, if you take a simple normal conductor, if you take a normal conductor, this normal conductor at every location has some resistance, 0.1 ohm, 0.1 ohm, like that. I told you, if you add total resistance, then let us say it is 2 ohm, then how you draw the equivalent of this? Equivalent of this is drawn like this. 0 ohm is there, this is perfect conductor, and total resistance if you add, you get 2 ohm, let us say. So 2 ohm, it is written like this. So for example, for this coil, na, it is open is there. Open means the resistance tends to infinity. And EMF also induced. So EMF not equal to 0. And here this EMF generates the current, but open is there. So current becomes 0. Then I square R energy. So here current is 0. So now that becomes 0. So heat loss, this is called as heat loss. This one, heat loss. Joule heat loss it is called as because resistance is there means heat loss is there. Joule heat loss is not there in this. Now I told you, if resistance is not given in examination for any loop, that you have to take it as a perfect conductor. You have to assume, nobody tells you that he has not given resistance means you should not assume resistance of your own, because every student assume different resistances. So you have to take this as a perfect conductor actually. So if you take this as a perfect conductor, now the resistance of this tends to 0. Now EMF induces actually. EMF definitely induces, but it is not having resistance. So the EMF induced tends to 0. And in this, current becomes not equal to 0 and finite it becomes. So student, it is like network theory. I is equal to V by R. Even very small resistance, even very small voltage in very small resistance produces finite current actually, like I is equal to V by R. R is very small, so huge current will be there, but infinity current will not be there, because no source can generate infinity current. So current is there, but it is finite actually. But resistance almost 0, because it is a resistance is not given means we have to take it as a perfect conductor. So for that resistance tends to 0. Now I square R. So current is finite, but resistance almost 0. Once again in this heat loss will be almost 0. In this also heat loss 0. Actually this is argumentative question, but you have to apply your common sense and solve this. If you see different books, na, you will get different answers. But if anybody takes more resistance for this, then answer will be different. R not equal to 0, EMF not equal to 0, I not equal to 0, then this also not equal to 0. That will be the answer. But what happens, students? In any question, the resistance is not given. You have to take that as a perfect conductor. For example, in network theory also, na, between the resistors, one conductor wire is there. For that conductor wire, you will be taking resistance as 0. For example, like this network is there, like this 10 ohm resistance, like this network is there. Here one wire is there. You will be taking resistance of this wire as a 0. You will never take some resistance to this wire in the network theory. So one resistor is there of 10 ohms. You will take that resistance. But for this wire, you will be neglecting the resistance. Similar to that, here also you have to take this as a very good conductor or otherwise perfect conductor. Then you have to analyze this one. Now, which of the following statements are correct? An EMF is induced in the split coil too. EMFs are induced in both coils. Okay. Equal Joule heating occurs in both coils. Joule heating does not occur in any coil. Yes, this is correct. 0 Joule heating, 0 Joule heating. So Joule heating does not occur in any coil. This is correct statement. Equal Joule heating occurs in both coils means he is saying heat is there. He is saying Joule heating occurs means heat is there, he is saying, but that is wrong statement. There is no heat here. So this is wrong statement. Now EMFs are induced in both coils. So dear student, this is also wrong. Why? For example, here let us say here more EMF is induced because resistance is more EMF is induced. Actually, EMF induces, but this has the ability to hold high EMF. So here EMF is very high, but compared to this EMF, here EMF is almost 0. So that is why you say EMF is induced in the split coil too, that is a good amount of EMF is induced, but EMFs are induced in both coils means compared to this here very small value, very negligible value is there. So that is why this statement and this statement both are correct. Okay. Now here one more question is there. A loop is rotating about the y-axis. For example, you draw the diagram here. Let us say this is x-axis. Let us say this is y-axis. One loop is there, maybe circular loop or rectangular loop, because loop shape is not given. You can take any shape of loop. So let us take rectangular loop. He is saying it is rotating about y-axis. It rotates like this. So, dear students, whenever loop is rotating, there is a motional EMF is produced in that. If there is resistance, then motional EMF is produced in that. So, and here the voltage, that means EMF. Voltage means here EMF in the loop is due to rotation effect, and also he has given here field B of t. It is a function of time he has given. So B naught cos of omega t plus pi ax cap. So it is a function of time here. If it is a function of time, then transformer EMF is also induced. So transformer action also present, and rotation effect, that is motional effect, is also present. So motional EMF as well as transformer EMF both are present. This is case 3 of the Faraday's law. Actually, case 1, case 2, case 3 are there. No, in a time varying magnetic field, whenever loop rotates or otherwise loop area changes, then motional EMF, that is called rotational here, and transformer action both are present here. This is the answer to this one. Okay, students. So, student, now let us see this question. If the electric field, it is a function of time, it is given, and epsilon is equal to 4 epsilon naught, then the displacement current carrying an area of 0.1 meter square at t is equal to 0 time will be. I was telling you, whenever displacement current is required and electric field is a function of time, we have to use this equation. JD of t is equal to dou d bar divided by dou t. Here dou by dou t means it should be a function of time. So d bar is a function of time. Now this JD of t is equal to actually ID of t divided by area. So displacement current by area is equal to, and d is equal to epsilon E. So epsilon into dou E bar of t divided by dou t. Now ID of t is equal to epsilon d by dt of, actually here scalar, that means direction is not taken, so you can take electric field magnitude here. Now epsilon d by dt of electric field is given as 0.1 t e power minus t. Direction is not taken, only magnitude is taken. Now this gives into here idea of t, area goes this side, so area came here, that area I have sent this side. So idea of t is equal to area multiplied with epsilon. D by dt of this one is 0.1 came out. This is a UV formula. So you get this is 1 into e power minus t plus t into d by dt of e power minus t is e power minus t minus 1. Okay. Now he is asking how much current is crossing some area. This one current is there, area is this side. So actually this is current density, student. Current density multiplied with area gives current crossing that area. That is the meaning actually. Now you have to find displacement current density at t is equal to 0 time. Substitute t is equal to 0 here. Then area is given as 0.1 meter square. So 0.1. And epsilon is given as 4 epsilon naught. So 4 epsilon naught. Okay. Then already 0.1 is there here, and substitute t is equal to 0. E power 0 is 1, and here t0 is there, t0. So this is the answer, dear students. Now this is a point 4 epsilon naught into 10 to the power minus 2. So this is the answer. Okay. Now this question you see, a straight conductor, this one, carrying a current carrying conductor, this one, a straight current carrying conductor, this conductor, and two conducting loops A and B, this is A, this is B. Actually, if I get out of the board, this is the conductor like this, and here one conductor loop is there, and here also one conductor loop is there like this. If the current in the straight wire is decreasing, that means he has given arrow mark like this. He has given I decreases in this direction. That is what given information. I decreases in this direction. Now the induced currents in the two types A and B will be, actually induced current in two loops I will write. No, they are loops actually. Induced current in two loops A and B will be. So in this induced current direction, in this loop induced current direction, you have to find. Now according to Lenz's law, if you put the thumb in current increase direction, then these closed fingers give magnetic field increased direction. Actually students, here if current decreases in this direction, then current increases in this direction. Now what right hand thumb rule says, if you put the, now for your convenience, I am getting this conductor here out of the board, and this loop is here like this. Okay, this loop is here like this. Now if I put the thumb in the current increase direction, then here one loop is there like this, and then this thumb is in current direction, current increase direction. These closed fingers are in magnetic flux density increase direction. So here this magnetic flux density line is in this closed line direction. So that is entering, this magnetic flux line is entering this loop. So here I will show, put the thumb in current increase direction, then magnetic flux enters this loop. Entering means into the board. Into the means symbol is used cross. This is B of T. So because of this current, I am using blue ink for them. Because of this current, magnetic flux or otherwise magnetic flux density is into the board in this loop. Now this loop is this side. Now here if I put thumb in the current increase direction, then magnetic field is, this loop is beside is like this, then magnetic field, this is straight conductor and this is the loop, then magnetic field is coming out of this loop like this. So coming out means dot, B of T. So dear students, original current is increasing like this, then original magnetic field is into the board, then out of the board. Now you have to use Lenz's law to find the induced current directions. What Lenz's law says, original magnetic field is into the board, then induced magnetic field is out of the board. So induced magnetic field is out of the board in thumb direction, then induced current is in closed finger direction. So in this induced current is in this direction. Induced current is like this. Original magnetic field is into the board. Induced magnetic field should be opposite of that according to Lenz's law. So I am putting the symbol for that. This B induced is opposite to the original magnetic field. Put the thumb in induced magnetic field direction, then induced current is in closed finger direction. Here also use Lenz's law. Original magnetic field is out of the board, then induced magnetic field is into the board. So B induced here. Now put the thumb in induced magnetic field direction, then induced current is in this direction. So this is the induced current direction. That means in loop A, induced current is like this, means this is clockwise, and here it is anti-clockwise. Okay, this is clockwise, that is anti-clockwise. In loop A, it is induced current is in clockwise direction. So here one more question is there. Consider coils C1 and C2 and C3, C4. Here coil C1 is given like this. So this is C1 coil, and C1 coil electric field here given, and C2 coil electric field is produced due to this current in the C2 coil, and C3 coil electric field here produced due to current in the C3 dash coil, and C4 coil electric field in this is produced due to current in the C4 dash coil. It is given in the question. Now already I told you one thing. If magnetic field is perpendicular to the coil, for example this is the coil, then magnetic field lines are coming like this, perpendicular to this, then EMF is induced in this coil. Now I told you facts, students. I am writing here, if magnetic field, that means magnetic field means magnetic flux, or otherwise B of t, or otherwise H of t, all are called magnetic field, is perpendicular to loop area, then EMF is induced in the loop. This is one point required to solve this question. And also, what is second point? Already I told you, student, electric field and magnetic field are perpendicular to each other. So these 2 points are required to solve this one. So what that fellow has given, you see here. Here there is electric field like this, time varying electric field, and this time varying electric field is parallel to the plane of coil 1. That means this electric field is parallel to plane of coil 1 as given, but magnetic field is perpendicular to this electric field. So E is perpendicular to H. That means here H is perpendicular to the plane of coil C1. So he has given electric field is parallel to the plane of coil 1, then magnetic field makes 90 degrees to the electric field. So magnetic field is perpendicular to the plane of coil 1. I wrote here, if magnetic field is perpendicular to the plane means area, plane, then EMF is induced. So in C1 EMF induces, he has given the electric field will induce. Actually here electric field means this electric field, time varying electric field generates time varying magnetic field, and if the time varying magnetic field is perpendicular to the loop area, then EMF is induced. So then electric field will induce EMF in which of the following coils? Then answer C1 coil it induces. These two answers gone. So C1 coil it induces. Okay, this coil also. So C1 it induces. So EMF is induced in C1 coil. That is correct. Now let us discuss here. Coil planes are orthogonal. The meaning is that one coil is like this and one coil is like this, students, this one. Other coil is like this. So this is the plane of the coil and this is the plane of the coil, and these planes are orthogonal to each other. That is the meaning of that. Coil planes are orthogonal here. Now if actually what happens, if this coil is like this, now in this current is going like this. Now you put the closed finger in current direction, then in thumb direction magnetic field is there. That magnetic field will be parallel to this coil here. So that is why EMF is not induced in this. So coil planes are orthogonal, then the current is there in this current generates magnetic field which is parallel to this one. So EMF is not induced. Now coming to this one, student. That means coil planes are orthogonal here also. Coil planes are orthogonal here also. That is why EMFs are not induced. You see here situation is like this. One coil is there like this. This one. C4. This is like this. Now these coil planes are orthogonal. Orthogonal means 90 degrees. Now in this one, current is going in the closed finger direction, let us say. Then current is going in the closed finger direction. Then magnetic field produced is in thumb direction. That is actually parallel to this one. If you see, parallel to this one, parallel. So here also it won't produce. Here you can understand very clearly. Coplanar, that means this coil is like this coil is also like this. Both coil planes are on the same plane. They are called coplanar coils. Now in this coil, now this is the coil, student, this one, and this is also this one. Now in this coil, current is going like this. Now you put the closed finger in current direction. A magnetic field is like this. Magnetic field is into the board. Now magnetic field lines are going like this. Magnetic field lines are closed lines. They go like this and again they come like this. Like this they will be going. So that magnetic field is perpendicular to this. So in this also EMF is induced, student. So in this also EMF is induced. Okay. So answer is C1 and C3 coils EMF is induced, dear students. Okay. Here H of t produced due to I of t is parallel to C2 coil area or otherwise plane. C2 coil area. So that is why EMF is not induced in this one. And same explanation for this also. So whenever coil planes are orthogonal, you remember, my dear students, after analyzing, whenever coil planes are orthogonal, then EMFs are not induced. If coil planes are same, then EMFs are induced. This is the answer. This is multi-select question. So in which of the following cases EMFs are induced? First case and third case. Multi-select question. This is multiple answers. Okay. So students, let us solve these questions. Already I told this diagram while explaining the Faraday's law cases. A circular turn, that means this one, of radius. So that means the radius of this rho is equal to 1 is given. So otherwise small r 1 meter is given. If you take this as a small r, so that is 1 meter is given. Revolves at, that means it rotates actually, revolves at 60 rpm. That means frequency is given as 60 rpm. That means 60 revolutions or otherwise rotations per minute it is given. So per minute means divide by 60 second, then you get rps. That means 1 rotation per second, or otherwise revolutions per second, or otherwise cycles per second. That is 1 hedge actually. F is equal to 1 hedge. About its diameter, it is rotating aligned with the x-axis. That means diameter is aligned with the x-axis. Yesterday I told you this is the loop. It is rotating like this, okay, as shown in figure. Mu naught is given. That means here in this mu naught medium is there here. Mu naught, the medium is air medium. If a uniform magnetic field intensity H, uniform means it is not a function of distance, you can see. So given H is equal to 10 to the power 7 AZ cap. Z cap means AZ cap, ampere per meter is given, is applied, then the peak value of the induced voltage we turn in this. I told you no need to explain anything. Yesterday I told you have to remember the case, and then if this diagram comes, then you have to use the formula I told you. So here the formula used is EMF is equal to, I told you na, this formula, EMF is equal to minus of B, because B is equal to mu naught into H is uniform, it comes out, area, and d by dt of cos omega t. Dear students, you see the notebook and that picture is there, you have to use this formula I told you. So here B is minus mu naught, because he has given mu naught is the medium present here, into H. For circular loop, area is pi r square, and d by dt of cos is minus sine omega t and omega here. So you substitute all things, minus into minus plus, mu naught is 4 pi into 10 to the power minus 7. H is given here, magnitude is 10 power 7, and pi r square, radius is given 1, so that is 1 square. Then omega is 2 into pi into f is 1 is given, then sine omega t. Okay, so 10 power minus 7, 10 power 7, 10 power 0 is 1, and 2 into 4 8, 8 pi cube, pi cube sine omega t is there. So this is the induced EMF, that is, he is calling that as a induced EMF, he is calling that as a V turn, and then maximum value is required. Peak value means maximum value here, so this is the maximum value, so V peak value this is, or otherwise EMF peak value, that is. So that is 8 pi cube is the answer. Okay, so answer is 8 pi cube. So if you solve this, you get this as a 248.05 volts you get. This is the peak value. Okay, now this diagram I have told you already. Whenever there is a loop, that loop here he has given, consider a one turn rectangular loop. This is rectangular loop of wire placed in a uniform magnetic field as shown in figure. So the magnetic field is uniform means that is not a function of time, but it is time varying magnetic field. In time varying magnetic field, whenever non-moving loop is there, in this EMF induces, for that resistance should be there. The resistance of the loop is given as he has given resistance as resistance is equal to 0.4 ohm for this loop he has given. Now he is saying the plane of the loop is perpendicular to the field lines, then only EMF induced, already we have discussed. So now the loop area is 10 centimeter multiplied with 5 centimeter. Okay, now omega is given here. The power absorbed by this loop due to this magnetic field, that means this magnetic field is into the board here. That magnetic field is crossing the area of this loop. Because of that, EMF is induced here, and that means voltage is induced here. Then power absorbed is equal to half Vm square divided by R. In network theory, if you know voltage maximum value, then half Vm square by R. If it is RMS, then simply Vrms square by R. No need to put half here. Simply you find EMF here. I told you for this EMF formula is equal to minus d by dt B of t into area. Now that is nothing but minus d by dt. Here B of t is 0.25 means 1 by 4 sine omega t into area is 10 into 5, 50 centimeter square means 10 to the power minus 4 you have. So that is minus 1 by 4 d by dt of sine is cos omega t into omega 50 into 10 to the power minus 4. So that is equal to minus 1 by 4. This is 2 into pi into f, that is given as 2 pi into 50 it is given. Then 50 into 10 to the power minus 4, and ultimately you have cos omega t. So this value becomes okay, this value is minus 0.3926 cos omega t. So this is the EMF. This is called maximum value of the EMF or peak value. This is Vm. Now power absorbed is equal to half into Vm square by R. Why half taken here? This is maximum value. So, dear students, half Vm square is 0.3926 whole square divided by resistance is given as actually 0.4 ohm. So now this power absorbed, this calculation becomes 0.1927 watts. This is the answer. This much power is absorbed by that one. Here, this question also I gave the formula for this. Whenever there is a radial magnetic field, so here B bar is there magnetically. A rotating conductor, that means this is the conductor. What is the length of the conductor? 1 meter. It is rotating like this with some rotational frequency. So it is given that length of the conductor is 1 meter. So 1 meter length is placed in a radially outward magnetic flux density. That means this is the magnetic flux density. This magnetic flux density is radially outward from the z-axis actually. So like this it is. That means B bar is equal to B naught into A rho. It is in cylindrical system. Already we have discussed this in the class of 1 Tesla. So B bar magnitude is actually 1 Tesla is given. 1 Tesla as shown in figure. Conductor is parallel to and at 1 meter distance from the z-axis. That means conductor is parallel to the z-axis is given, and it is at 1 meter distance. That means radius is 1 meter. So he has given radius is equal to 1 meter. Now the speed of the conductor in rotation per minute, that means you have to find frequency in rotations per minute required to induce a voltage of 1 volt. That means here EMF is induced in this. How much EMF induced? So EMF induced is equal to 1 volt. So to induce 1 volt EMF in this rotating conductor, then what should be the rotations per minute? That means frequency you have to find. So I told you, dear students, if you observe carefully, this conductor is rotating like this. That means the velocity is r omega into a pi. Then B bar is in rho direction. Then L bar is in z direction. B bar, L bar, and V bar velocity, they are mutually perpendicular. Then EMF induced is equal to VBL. I told you, see the notebook, nothing is there to see here. I told you this picture comes, use this formula. I told you R omega into BL. That means radius is given as 1, then 2 into pi into F. Anyway, let us write this one. B into L, EMF is equal to, we want F, so that is equal to EMF divided by R into 2 pi into B into L. Now substitute the quantities. EMF required how much? 1. R is 1, 2 pi. Then B is given 1, L also 1. So this is rotation per second, student. So RPS this is. Now if you want this is 1 by 2 pi, you can put 60 by 60 here, then rotations per second. That means per second is there, 60 seconds becomes minutes, so this is 60 by 2 pi RP. This is 60 seconds, na? I will write like this, rotations per second. Okay. Now this 60 second, 60 divided by 2 pi, 60 second is taken as per minute, so rotations per minute. So this is the answer. 30, this is 30 by pi rotations per minute. So this calculations, this calculation becomes 9.549 rotation per minute it becomes. Okay, this is the answer. Okay. So dear students, now uniform plane wave chapter, let us solve some questions from time varying fields. So those time varying fields questions are given in this chapter, workbook chapter 3. So first question is already solved, second one is solved, third one is also solved, fourth one is also solved. Now let us solve the fifth one. So chapter 3, fifth question. I am writing the question actually. So in the workbook, if question is there for GATE students, this question is not there, but I am writing the question. If the magnetic flux density, if the magnetic flux density of a point in a region is 250 sine 120 pi t, Az cap milli Weber per meter square. Okay. What is the curl of the electric field intensity? So, what is the curl of the electric field intensity? So, this is the question. This is a very simple question. So, del cross E bar is equal to minus of dou V bar by dou T. So, minus of dou by dou T of B bar is given here 250. Here milli means 10 to the power minus 3 and then sine 120 pi t. So here dou by dou t means partial differentiation with time, but anyway here no distance, so you can write d by dt also, no problem. So that is del cross E, curl of electric field is required. So that is minus 250 into 10 to the power minus 3. D by dt of sine is cos 120 pi t into 120 pi. Now this is the answer. Anyway, here na B bar z direction is there for this. Okay, so here Az cap comes, you multiply this. So this is the answer, students. Now next question. For GATE students, the question number may be different, but anyway I am writing the question, don't bother about that. The vector magnetic potential, the symbol is capital A bar, already you know that, of a particular wave traveling in free space, that means air medium, is given by A bar is equal to Ax, this is the magnitude, sin omega t minus beta z Ax cap, where Ax is constant as given. The expression for the electric field will be, the expression means equation, the expression for the electric field intensity actually. So electric field intensity, he has not given intensity, but that is electric field intensity is, you have to write the equation. So this is standard formula, I am writing that here. So you students know that Maxwell equation, del cross E is equal to minus dou B bar by dou T. This is equation number 1. Now how this vector magnetic potential is defined? If A bar is vector magnetic potential, then B bar is equal to del cross A bar. Now put equation 2 in 1, then del cross E bar is equal to minus of dou by dou T. This B bar is written as del cross A bar. Now this del is a function of xyz, dou by dou x, dou by dou y, dou by dou z. So d by dt can go inside because there is no time here. Now del cross minus also can go, minus dou a bar by dou t. So this is del cross E. So del cross E bar should be equal to this one. Compare both sides. Now E bar is equal to minus of dou A bar by dou T. This is standard formula you have to remember. Given vector magnetic potential, unit is Weber per meter. Already you know that. If you differentiate that and minus of, then you get electric field intensity. So he has given A bar here. You have to find electric field intensity. So here A bar is given here. Ax, that is constant. Actually he has given here Ax is a constant. It is given in the question. That is magnitude actually. So Ax sine omega t minus beta z Ax cap. So this is minus Ax. D by dt of sine is cos omega t minus beta z. You differentiate with the time means omega comes here. So Ax cap. So minus Ax cap omega Ax cos of omega t minus beta z. Option D is correct. So option D is correct. Now next question. Which of the following is the correct electromagnetic wave equation in terms of vector potential? Vector potential means that is vector magnetic potential, A bar. So in the options d by dt you are seeing and the equations are in terms of A bar and J bar. So d by dt means for time varying fields you have to see. So let us write the equation of time varying fields. Now this is also standard question. Now we know that one of the Maxwell equation del cross h bar is equal to J bar plus dou d bar by dou t. Now this is for time varying fields. In the options dou by dou t is there. That is why we have selected this one. So J bar plus d bar is epsilon E bar. So epsilon dou E bar by dou t. Let us say this is equation number 1. Now we know that E bar is equal to, in the previous question you have seen, in terms of vector potential, E bar is equal to minus dou A bar by dou t. So equation number 2. And B bar in terms of vector magnetic potential is B bar is equal to del cross A bar. So B bar is this one mu into H bar. So del cross A bar. From this H bar is equal to 1 by mu into del cross A bar. So equation number 3. Now put equation 2 comma 3 in 1. Then del bar cross 1 by mu into del cross A is equal to J bar plus epsilon dou by dou t minus of E bar is equal to minus dou A bar by dou t. Now if you take medium as homogeneous medium, homogeneous means mu is not a function of xyz, it can come out. So 1 by mu and del cross A bar, so that is equal to J bar, and here minus comes out, minus epsilon. This is dou square A bar divided by dou t square. So double differentiation is there with respect to time. Now here let us say this is equation number 4. Let us expand this. Already you know this. A bar cross B bar cross C bar expansion is A bar dot C bar of B bar minus minus A bar dot B bar of C bar. According to this, if you expand this one, then 1 by mu del bar dot A bar of del minus del dot del of A bar. This is equal to J bar minus epsilon dou square A bar divided by dou T square. Already in the magnetic chapter I told you divergence of B0, that means this is Weber per meter square. This magnetic, if it is north pole, south pole, magnetic flux lines are closed lines. The unit of that is Weber. If magnetic flux line is a closed line, then divergence of that magnetic flux is 0. Divergence means going away, but this is not going away. It is going, but again coming back. So divergence of this magnetic flux is 0. Divergence of magnetic flux density is also 0, and divergence of vector magnetic potential also 0, because this also has unit Weber per meter. Wherever Weber unit is there, divergence of that quantity becomes 0. So you substitute this one here. Now you get 1 by mu 0. This del dot del is del square A bar is equal to J bar minus epsilon dou square A bar divided by dou T square. Now in the options, he has sent this mu this side. So what you do, here minus of you take, so mu send this side, student. Now it becomes a del square A bar minus of is equal to mu into J bar, then minus mu into epsilon dou square A bar divided by dou T square, and he has kept this one side. So he has written positive for this. That means you send this side, you send this side. That means ultimately it becomes a del square A bar, I brought this side, and minus mu epsilon dou square A bar divided by dou T square, and you send this side minus mu J bar. So this del square A bar minus mu epsilon dou square A bar by dou T square is equal to minus mu J bar. So this is the Poisson equation of magnetic fields, Poisson equation of time varying magnetic fields, or of course electric field also. So this is Poisson equation for time varying electromagnetic fields, this one. So if it is static field, d by dt becomes 0. Already we have written del square A bar is equal to minus mu J bar, we have written in the static magnetic field chapter. For static magnetic field, d by dt term becomes 0. So then del square A bar is equal to minus mu J bar. I wrote in the static magnetic field that has a Poisson equation of magnetic fields I wrote. So this is also Poisson equation of time varying electromagnetic fields. This is one of the standard question in the objective questions. Okay, students. So dear students, let us talk of harmonic functions. Function means one equation. Harmonic means repetitive. So function means equation. Harmonic means repetitive actually. It should repeat periodically. So here periodic means repetition. So for example, a e power j theta, you take a into e power j theta is cos theta plus j sin theta. So that is nothing but a cos theta plus j into a sin theta. So this is one function, that means that is equation. This is another function. So they are periodic actually. So for example, if you take on the y axis, you take a cos theta, and here on this axis you take theta variable, and similarly here okay, I will reduce the size of this anyway. So here if you take this as a a cos theta and this is theta. And similarly here you take this as a sin theta and this one is theta actually. So dear students, you know that cos signal variation is like this cos signal, and sin signal variation is like this. Sin signal variation is like this. Now here this is plus a and this one is minus a. Similarly this is also plus a and this one is minus a. Of course this is symmetric, students. Top side and bottom side equal height. Okay. Now here repetition, you see here this value is repeated here again. That positive plus a, this positive plus a repeated. So that is called a repetition angle. That repetition angle is actually 2 pi radians. So here it is actually pi radians. Similarly here if you see carefully, here if you see the starting one is 0 and again it is repeating here, that starting value 0 value. So here it is 2 pi and here it is pi, it is 0 angle here. So here 2 pi is called as actually theta means angle. When theta is 0, here you got 0 value. Again when theta becomes 2 pi, then again that value is repeated here. Repetition other name is period. So the angle period is 2 pi radians. Dear students, now angle period is 2 pi radians. So these are periodic functions. They are called as harmonics. Harmonics means repetition is there. Now for example, if you take a into e power j omega t, so that is nothing but a cos omega t plus j sin omega t. Here what is the omega t? Here theta is called actually phase. Theta is called phase. Phase means it is measured in radians, that is related to the angle actually. Omega t, in place of theta here omega t is there, so it is also phase. So it is also phase, but time is there. So this phase is coming due to change of time, so it is called as time phase. For example, the minimum value of theta is 0 and again repetitive value of theta is 2 pi. So when t is 0, then time phase omega t is equal to 0. When t is equal to capital T time, then if time phase omega t becomes 2 pi radian, then capital T is called as time period. Here dear students, period means repetition. In the time it is repetition, so capital T is called as time period. So that means this is another statement. Whenever t is 0, then time phase is 0. If t, whenever you substitute t is equal to capital T, then if this time phase omega t becomes 2 pi radians, then it is called as a time period. So that means whenever omega t, whenever t is equal to capital T, then if the total phase time phase becomes 2 pi, then capital T is defined as a time period. So this is the formula actually. So that means omega is equal to 2 pi by capital T. So that is also written as 2 pi. 1 by T is frequency. So here, if you draw this, this is A cos omega T. Now you will be taking here a time axis. Now cos signal is like this. Cos signal is like this. Okay, like this it comes. So this is plus A, and this one is minus A. Now here, this is time axis we are taking. Then here plus A value. Again when you come here, that is value is becoming plus A. So that means this is the repetition of the time called capital T. This is half of that. So this is T by 2 it becomes. So this is 0 time. So dear students, this is the time axis. Then time repetition is capital T here. This is phase axis, angle axis. Phase means angle actually. So here repetition is actually angle. Here angle is repeating. Here time is repeating actually. So dear students, similarly, I am not drawing the sine signal. It comes similar to this one sine signal, but what do you say? Time will be repeating there. Now, if you take A e power j beta z, that is nothing but A cos beta z plus j into, here also A should be there, otherwise you do like this, okay, cos beta z plus j sin beta z student. So here see this one, A into e power j theta. Theta is actually angle, or otherwise it is also called as a phase. Here omega t is also phase, but because of time it is coming, so it is called time phase. But here beside j, beta z is there, so this is also phase actually, but this is because of distance z it is coming. So here beta into z is called distance phase. That means phase means angle. That angle is coming because of change of distance actually, so it is called distance phase. When the distance 0, then distance phase becomes beta z is equal to 0. That is the 0 radian is the starting angle. Okay. When, for example, z is equal to lambda meters you travel, then if distance phase, that is actually beta z, becomes 2 pi radian, then lambda is called as distance period. Distance period means repetition. So repetition of the distance. So distance period. This is also called as wave length. Length means distance actually. When wave travels lambda distance, then automatically distance period is repeated. That angle will be 2 pi radians actually. This is definition student. So here that means whenever z is equal to lambda meters distance, then if phase becomes 2 pi, then this lambda is defined as a distance period or otherwise wavelength. So this is the definition student. So from this beta is equal to 2 pi divided by lambda. Okay. Here lambda is called what, dear students? So lambda is called as a distance period or otherwise wavelength. Okay. So now Coming to the name of beta, so for a particular case lambda is constant, 2 pi is also constant, beta is also constant. This constant tells you, that means beta. Beta tells you how phase changes with respect to distance. So that is why beta is called phase shift constant. That means beta into z is actually phase. Now this beta tells you, actually beta is a constant value. Later on we will discuss that. Beta is a constant value. Then this constant value decides how phase changes whenever z is variable. Then phase also variable. For example, students, if beta is 0, then there is no distance phase at all. So if beta is not equal to 0, then beta z is distance phase. Now in this, if distance changes, this distance phase also changes. This is variable symbol. Because of this only, if distance is changed, distance phase also changes. So that is why beta is called phase shift constant. Okay. So here angle harmonic is there, time harmonic is there, and distance harmonic is there. So here if you draw that A cos beta z, that is nothing but A into cos beta is 2 pi by lambda into z. So if you draw the, here z is to be taken on this axis, so cos signal is like this. Now here if you take A, you can see here students, at z is equal to 0, at z is equal to 0 distance, this A cos 2 pi by lambda into, it is 0, so that is A cos 0, that is equal to A. That means whenever z is equal to 0, on this distance axis we have taken. Now this is actually repeated value. Now for example, at z is equal to lambda by 2 distance. So this will be lambda distance and this will be lambda by 2 distance. Let us see now at lambda by 2 distance, A cos 2 pi by lambda into z is lambda by 2 now. Now A into cos of lambda lambda cancel, you get cos pi. So cos pi is minus 1, minus A you get. So whenever z is equal to lambda by 2, then this value becomes minus A. Now at z is equal to lambda distance, then this A cos 2 pi by lambda into z is equal to lambda you substitute. So lambda lambda cancel, A cos 2 pi, that becomes A. So whenever z is equal to distance is equal to lambda, then again this value is actually I would take symmetric, student, don't bother about that. Symmetric, this is symmetric actually. Okay. So this is plus A. So the conclusion is that A cos beta z, here A cos omega t and A cos theta all repeat. They are harmonic functions. But in case of A cos theta, this axis is angle, that angle period is 2 pi radians. In case of A cos omega t, this axis is time axis. So here repetitive time is, or otherwise time period is capital T. In case of A cos beta z, this axis is distance axis. The repetitive distance is also called as wavelength, is lambda here. Okay. So dear students, in the uniform plane waves, let us derive the wave equations, or otherwise Helmholtz equations, wave equations, or otherwise Helmholtz equations. Okay. Now, whenever EM wave travels, for example, let us say here antenna is there here. From this antenna, EM wave is released and it travels in this medium. Now, this medium is, for example, air medium. In this medium, parameters are epsilon, mu, sigma. In general, these epsilon, mu, sigma parameter values do not change from location to location. That means epsilon, mu, sigma values are constants. If epsilon, mu, sigma values are constants, then we call that medium as a homogeneous medium. So for homo means same, genus means type, homogeneous medium means same type of medium. In that medium parameters called epsilon, mu, sigma values do not change with respect to distance. So they are not function of x, y, z. So they are constants. In any medium, if epsilon, mu, sigma values change with respect to distance, that means they are functions of x, y, z, then that is called not same type of medium. So that is called non-homogeneous medium. So here for homogeneous medium, for homogeneous medium, epsilon, mu, sigma are constants. That means epsilon, mu, sigma are not functions of x, y, z. And for homogeneous medium, epsilon, mu, sigma are constants actually. So, but for if you talk of non-homogeneous medium, for non-homogeneous medium, epsilon, mu, sigma are functions of x, y, z. Okay. Now, if you see isotropic medium, iso means same, tropo means direction. Isotropic medium. In isotropic medium, epsilon, mu, sigma values do not change with direction. For example, air medium, in any direction, in x direction, y direction, z direction, in any direction, these values are same. That is called isotropic medium. I will write like this for isotropic medium. Okay. So similarly, for non-isotropic medium, epsilon, mu, sigma values change with respect to direction. Dear students, for example, diamonds are there. In diamonds, shine or glitter in different ways in different directions. In those crystalline materials, epsilon, mu, sigma values change direction to direction. But whenever EM wave travels, here air medium is present, and for example, cement wall comes, These mediums are isotropic mediums, and in those mediums, direction to direction, epsilon mu value sigma doesn't change. Now, coming to the linear medium. Which medium? Linear medium. For linear medium, for linear medium, J is equal to sigma E, D is equal to epsilon E, P is equal to mu H. Equations are valid. That means for linear medium, these three parameters follow y is equal to mx equation, y is equal to m into x, y is equal to m into x, y is equal to m into x. Linear equations are followed. But for nonlinear medium, these equations are not valid. For non-linear medium, the above equations are not valid. Okay, students, these equations are not valid. Next, source free or otherwise charge free. So, charge free region. That means in the volume, charge is not there, then that rho v is 0. Charge free region or otherwise charge free medium. So, medium has volume. In that volume, if charge is not there, then rho v is 0. Charge free region, for charge free region I will write. So, for charge free region, rho v is equal to 0, because for charge free region or otherwise medium, medium has volume. In that volume, if there is no charge, then volume charge is equal to 0, dear students. For example, when EM wave travels in the medium, generally you will not find any volume charge. That is the meaning. So now we are talking of equations of EM wave. Wave equations means electromagnetic wave equations. So they're also called Helmholtz equations. Now we have four Maxwell equations. We have four general Maxwell equations. General Maxwell equations means they are applicable for all the cases. Okay. Now, whenever there is an antenna here, for example, then EM wave travels in the medium, in air medium. After some time, it hits the wall, cement wall. Then EM wave crosses that EM wall, because in that cement wall also epsilon mu is there. If epsilon is there, electric field is transferred. If mu is there, magnetic field is transferred. Then if sigma is there, conduction current is also transferred, dear students. So, wherever our EM wave travels, there exists a medium. That medium is a homogeneous medium, and that medium is isotropic medium. That medium is linear medium, and also charge-free medium, that is. So by taking these conditions, we are going to derive the wave equations. Okay, electromagnetic wave equations. Now, here we are starting the Helmholtz equations. Let the until this just I gave general information. Okay, let the medium is homogeneous, comma, isotropic, comma, linear, and charge free. Charge free, that means rho v 0. Then For this medium, Maxwell equations become one by one. I will write. First Maxwell equation, general equation is del cross E is equal to minus of dou B by dou T. Now, del cross E, that is general equation. If it is linear medium, B bar is equal to mu into H is written for linear medium. Now this mu comes outside. If mu comes outside, then del cross E is equal to minus mu into dou H bar by dou T, equation number 1. Now second general equation, general मतलब हर जगह वैलिड है वो. So del cross H bar is equal to J bar plus dou D bar by dou T. This is the equation. Now for linear medium, J is equal to sigma E, D is equal to epsilon E. D is equal to epsilon E. Now del cross H is equal to sigma E plus epsilon dou E bar by dou T, equation number 2. Now third one, this is general Maxwell equation and this equation is valid for linear medium. Now third Maxwell equation is divergence of D is equal to rho V. For linear medium, D is equal to epsilon E, and for charge free medium, rho V is 0. And once again, for homogeneous medium, epsilon is constant, so it can come out of the del now. It comes out of the del because del has dou by dou x ax, dou by dou y ay, dou by dou z az. So it is a function of differentiation with respect to x comma y comma z. So it is constant, it can come out. Now epsilon is equal to 0. So divergence of E bar is equal to 0. So this is equation number 3. Fourth one. Divergence of B bar is equal to 0. This is the fourth general Maxwell equation. Now for linear medium, B is equal to mu H. Then again for homogeneous medium, mu is constant. Mu is constant, so it can come out. If it comes out, then divergence of H bar is equal to mu into del dot H bar 0. So ultimately you send this side is equal to 0. This is fourth equation. So dear students, whenever we consider medium as a homogeneous, isotropic, linear and charge free, then Maxwell equations become like equation 1 and 2 and 3 and 4. ये ऐसा नहीं है स्टूडेंट, अच्छा लगता है इसलिए हम लोग मीडियम को होमोजेनियस, आइसोट्रोपिक, लीनियर, चार्ज फ्री नहीं ले रहे हैं. सच में जो मीडियम है, ईएम वेव ट्रैवल करता रहता है, वो मीडियम है. सच में होमोजेनियस मीडियम भी रहता है, आइसोट्रोपिक भी रहता है और लीनियर भी रहता है और चार्ज भी नहीं रहता है उस मीडियम में. इसलिए वो कंडीशंस लेके हम लोग डेरिवेशंस कर रहा है. वेव इक्वेशंस मतलब क्या है? Electric field equation and magnetic field equation of the electromagnetic wave are called wave equations. So dear students, wave equations means, here wave means electromagnetic wave. Electromagnetic wave transfers energy from one location to other location using electric and magnetic fields. Once again I am telling, electromagnetic wave travels energy from one location to other location in the form of electric and magnetic fields, dear students. So Now we need one equation. For example, in this equation, if you see, this side electric field is there, this side magnetic field is there, but both sides electric field is not there. Similarly, here also magnetic field is there, electric field is there, both sides magnetic field, electric field is not there. One side magnetic field, other side electric field is there. Now how to get both sides single quantity called electric field? Now we will do that. Okay, so here take curl of equation 1 both sides. Okay, now if you take curl, del cross E is equal to del cross minus mu into dou h bar by dou t. Now if we expand this like A bar cross B bar cross C bar formula, we get del dot E bar of del bar minus del dot del bar of E bar is equal to minus mu, because for homogeneous medium mu is constant, it can come out of the del. Once again I am telling student, for example, if it is like this, for example, if it is like this, now here this del is dou by dou x ax plus dou by dou y ay plus dou by dou z az. So it is differentiation with respect to x comma y comma z. If it is a function of x y z, then you cannot get this outside. But if mu is constant, then it can come out of this. Okay, so you remember, if for homogeneous medium mu is constant, it can come out of this del. But for non-homogeneous medium, mu is a function of x y z, so it cannot come out of the del, students. So now we are talking of homogeneous medium, mu can come outside. So minus mu, minus nothing is there, it is not a function of x y z, so minus mu can come outside. Now here d by dt also can come outside this, because d by dt means differentiation with time, but it is not a function of time, so it can come out. So ultimately you get dou by dou t of del cross h bar, students. So in this equation, let us call this equation as a 5. In this equation, from equation 3, divergence of E is equal to 0, you substitute this one, this becomes 0. Now del dot del becomes del square E, and del cross H formula is there here in terms of electric field. So you have to put equation 2, that means this one, that equation del cross H is in terms of electric field here, and equation 3, put 2 comma 3 in equation number 5, then we get both sides electric field actually. Okay, now so here it becomes 0 minus del square E bar is equal to minus mu into dou by dou t of del cross H is sigma E bar plus epsilon dou E bar by dou t, students. Now minus minus gone, so ultimately del square E bar is equal to, this is mu sigma dou E bar by dou t plus this is mu epsilon and d by dt, so 2 times dou square E bar divided by dou t square. So this is equation number 6. Here it is a differential equation. Del square is nothing but dou square by dou x square. Now it becomes like this. So dou square E bar by dou y square and dou square E bar divided by dou z square is equal to this one. So you must understand, this is a differential equation of electric field. with respect to x comma y comma z, and time also is there. If you solve this one, you will get the electric field equation in terms of x comma y comma z comma t. Okay, students. So just like that, I wrote here this del square E. Solution of equation 6 is E bar in terms of x comma y comma z comma t. So that means electric field equation is a function of x comma y comma z comma t. So here in the differential equations, bottom side x, y, z, t are there. They are called independent variables. So here solution is upper quantity, that is electric field in terms of independent variables x comma y comma z comma t. So there are 4 independent variables. So it is very difficult to solve this one. So that is why we suppress the time in next step. Suppressing time means we try to write this equation in steady state. Then we will assume that wave is traveling in z direction. Then in that case, electric field will be a function of z only. Then we will be solving that one. So anyway, solution of equation 6 is E bar in terms of x comma y comma z comma t. So this gives equation 6 gives E bar equation of electromagnetic wave. So it is called as electric wave. So it is called as electric wave equation. So this equation, solution of this gives electric field equation. That electric field belongs to the electromagnetic wave. That is why this is called as electric wave equation. So this equation is called electric wave equation. For example, in objective questions, which of the following is the electric wave equation? If they ask, this is the answer. So that is why you put this in the box, dear students. Del square E bar is equal to mu sigma. Mu sigma is there single differentiation, and mu epsilon is there double differentiation. Because mu means inductor. In inductor formula you get one differentiation. Epsilon means capacitor. In capacitor also you get one differentiation. So two differentiations are there. Here mu means inductor, you get one differentiation. Sigma means resistance. V is equal to IR. In that formula there is no differentiation. So single differentiation is there. Now similarly, you take a curl of equation 2 both sides. Then equation 2 del cross h bar is equal to del cross sigma E plus epsilon dou E bar by dou t. So equation 2 is del cross h is equal to sigma E plus epsilon dou E by dou t. Now both sides I have taken curl. Once again you expand this one from the formula A bar cross B bar cross C bar. So that is del dot h bar of del minus del dot del bar of h bar is equal to, for homogeneous medium, sigma is constant, it comes out. So sigma into del cross E bar, next plus epsilon comes out, then del is not a function of time. So dou by dou t of del cross E bar. Okay, like this. Let us say this is equation number 7. Now From equation 4, del dot h is equal to 0. Then del dot del is del square h bar. Then del cross E in terms of h bar is present in equation number 1. So substitute equation 1, put equation 1, comma 4 in 7. Then it becomes a 0 minus del dot del is del square. So del square h bar is equal to sigma into this del cross E is minus mu into dou h bar divided by dou t, and plus epsilon dou by dou t of del cross E is minus mu into dou h bar by dou t. Now minus cancel. So ultimately you get del square h bar is equal to mu sigma then dou h bar by dou t plus mu epsilon. Mu here, mu is there, epsilon is there, double differentiation is there. So dou square h bar divided by dou t square. Here equation number 8 this is. You should understand this equation number 6 and equation number 8 both are similar, because if you replace E bar with H bar in equation 6, then you get equation 8. So both are similar equations. Now the solution of this equation is H bar in terms of x comma y comma z. That H bar equation is magnetic field equation for electromagnetic wave. That is why this is called magnetic wave equation. Magnetic wave equation means if you solve this, you get H bar equation. That H bar is magnetic field intensity of electromagnetic wave. So that is why it is called a magnetic wave equation. Now equation 6 and equation 8 together called as wave equations, or otherwise they are also called as Helmholtz equations. This is one of the conventional question. In that conventional question they ask derive the Helmholtz equations, or otherwise derive the wave equations. This is the derivation. You have to start with Maxwell equations and you have to derive equation 6 and equation 8. Now this is the derivation of wave equations and Helmholtz equations. Now dear students, here I will write that statement here. This is also, h bar is also function of x comma y comma z comma t. 4 independent variables are there. I told you if so many variables are there, it is difficult to solve that one, right? Okay, so I will be writing there. So students, solution of equation 8 is h bar in terms of x comma y comma z comma t. So it is called as magnetic wave equation. That means this h bar is magnetic field for wave, that means electromagnetic wave. That is why it is called magnetic wave equation. Now equation 6 comma equation 8 together, दोनों मिला के together are called as wave equations, or otherwise they are also called as Helmholtz equations. Okay, after this we will talk of phasor domain, how to suppress the time, we will talk of that. Okay.